Why do we have the experience of being conscious? Can you build consciousness just by putting together lots of neurons in the right way? Or might there be deeper principles at work? Could quantum physics have something to do with the brain and specifically with consciousness? Is it possible that consciousness is actually something that predates biology, and there's a sense in which biology evolved to take advantage of it? And what are the right ways to make new theories in neuroscience when we don't know the answers? Welcome to Inner Cosmos with me, David Eagleman. I'm a neuroscientist and author at Stanford, and in these episodes, we sail deeply into our 3-pound universe to uncover some of the most surprising aspects of our lives. Today's episode is about consciousness and quantum mechanics and the question of whether there could be, even possibly, any connection between them. So to get at this, I'll be talking today with Roger Penrose, mathematical physicist and polymath and winner of the 2020 Nobel Prize in Physics, and also Stuart Hameroff, an anesthesiologist who has collaborated with Penrose for many years on a theory. Before we dive into those interviews, I want to set the table by saying that what we're going to talk about today are speculative ideas, and many neuroscientists don't even like to go near them. But the fact is that despite the thousands of neuroscience journals and textbooks and laboratories, there are still fundamental, basic questions that we don't know the answer to. And one of the most fundamental is the question of consciousness. Why does anything feel like something? In other words, imagine that you built a little toy out of pulleys and levers and switches. Would you say that it is conscious? Presumably you wouldn't. Now, double your little toy in size with new levers and switches and pulleys. Is it conscious now? There's no particular theoretical reason to think so. Now keep adding to it. Put on another pulley and another lever and another little door and attach a wheel, and keep doing this until you fill a room and then a stadium. Do you have any reason to assume that it becomes conscious and has internal experience just because it's more and more complex? If you now remove a pulley, does it feel pain? And if you put a little molecular detector on it such that it can recognize molecules of different shapes, does it have a different experience, like displeasure for some shapes and pleasure for other shapes? And where is that happening? I certainly wouldn't think that your giant toy is conscious, or at least let me say that I have no theoretical reason to believe that it suddenly experiences pain or hunger or longing or pleasure, because it's just pieces and parts. So this is a fundamental question about the brain. We look at your 86 billion neurons, which are generally thought of, especially now in this era of AI, as being units that are popping either on or off, 1 or 0. And so it's not clear to any of us in neuroscience why we have private, subjective experience. And this is true whether you have 86 neurons or 86 billion or 86 gajillion of them. Why do these little electrical signals and chemical releases give us the experience of eating a lemon, or the pleasure of an orgasm, or the pain of stubbing your toe? Now, we don't know the answer, but here's a speculation that some people have put forward. Could consciousness, the most intimate, subjective, elusive feature of our existence, have something to do with quantum physics? Now, this is not a mainstream idea in neuroscience. You're not going to find it in the standard textbooks. Most cognitive scientists, if asked to explain consciousness, will talk about neurons and synapses and the emergent properties of complex systems. The language will be biological and electrochemical and computational. But a few scientists have suggested a hypothesis that there's something deeper going on, something much stranger, and that's what we're going to explore today. I'm not presenting an argument that quantum mechanics does explain consciousness, but it's worth understanding why some serious minds are entertaining the hypothesis. So we'll begin with Roger Penrose, who is perhaps an unexpected figure in this conversation because he's not a neuroscientist. He's a mathematical physicist. He's done so many amazing things in his career. He worked with Stephen Hawking on black hole singularities, or you might know him for his geometrical shapes called Penrose tiles. And you certainly know him because in 2020, he won the Nobel Prize in physics for showing that black holes result naturally from Einstein's general theory of relativity. And by the way, he's also the one who mathematically described black holes in detail, including their singularity where all known laws of nature dissolve. But especially in the 1980s and 90s, Roger Penrose turned his attention toward the brain. Not because he wanted to build a better theory about cognition, but because he had a concern about algorithms. Penrose felt that consciousness just can't be explained by any rule-based system. He pointed to an idea called Gödel's incompleteness theorem, which said, look, there are mathematical truths that we can see to be true, but they can't be proven within mathematics. In other words, there are many systems where we can see things to be true, but the system itself can't prove them. You need to somehow step outside of the system. Now, to Penrose, this was a sign that human understanding operates in a way that transcends computation. In other words, he said, brains aren't just computers. And if they're not just computers, then the mystery of consciousness might demand a different kind of physics. So he wrote a very interesting book called The Emperor's New Mind, which asserted that the brain can't just be a computer. So in your book, Emperor's New Mind, which I read as a young person and really loved, you argue that consciousness can't be explained by algorithms. So help us to understand that.
But it really means, you see, an algorithm is just a sort of technical word for a computer program, if you like. Maybe people use that term. It just means that you have a rule, which is a computational rule.
Right. And what made you feel that consciousness can't be explained by algorithms?
Well, it goes back to the lecture that Steen gave about Gödel's theorem. And I realized that, you see, mathematical proof, you could have a set of rules, axioms and rules of procedure, and these are of a nature that you could put them on a computer.
Do you think there are forms of human insight that fundamentally cannot be replicated by algorithms? That's
correct. Yes.
Okay.
Yes, absolutely right.
Okay,
yes.
Great. And so that made you think that maybe this mystery of consciousness needed to be taken seriously by physicists and mathematicians. So
yes.
So how did you start addressing this?
You see, I was trying to think about the laws of physics that we sort of understand, and some of them are very powerful. Well, even Newtonian mechanics explains an awful lot. Einstein's general theory of relativity explains a lot more. And it's more difficult to apply things, but it's still computational. What about quantum mechanics?
Now, before we go further, I just want to give a reminder about what quantum physics is. It's the branch of physics that describes the behavior of matter and energy at the smallest possible scales, at the level of atoms and subatomic particles. And down there, the world behaves nothing like what we're used to. Particles can be in more than one place at once. This is what's known as superposition. Particles can become mysteriously linked across space in what's called entanglement. And the most bizarre feature of all is that the mere act of measuring a system seems to affect its outcome. This is what's called the observer effect. In our current understanding of quantum mechanics, the story is that until a particle is observed, its properties don't exist in a definite way. They exist only in probabilities. In other words, a quantum particle doesn't have a precise location until you look at it. Until that moment, it's smeared across a range of possibilities. And then those possibilities collapse to one outcome when you observe. Now, this isn't just a metaphor. This general idea has been tested and confirmed for over a century, and it's built into the fabric of our technology. Quantum mechanics is the science that allows the transistors in your cell phone, and the lasers at the grocery store scanners, and the GPS in your car. Quantum mechanics is real, and it's very counterintuitive, and it seems to tell us that at the heart of reality is a kind of indeterminacy, a fuzziness that only collapses into certainty when it's observed. So think of it roughly this way. You toss a coin in the air, and while it's spinning, it's not heads or tails. It's sort of like it's both at once. But the instant you catch it and look, it becomes just one, heads or tails. That moment of catching it is like the wave function collapsing. Now here's the thing, in quantum mechanics, there's no way to predict what the coin's going to be, heads or tails. And so that non-computable strangeness, that's what Penrose was interested in. He wondered, what if that indeterminacy, that collapse of possibilities into one real outcome, wasn't just a physical process, but also has to do with a mental one. In other words, what if the flicker of consciousness is related in some way to the collapse of the quantum wave function? So back to Penrose talking about his search for something non-computable and getting interested in the collapse.
What about quantum mechanics? Then I thought, well, the Schrödinger equation, there's no problem about putting that on. There may be lots of parameters involved which make it tricky, but that's a well-determined deterministic equation. But the Schrödinger equation doesn't give you what happens in the world. Why doesn't it give you what happens? Schrödinger himself was very keen on explaining these things. And his well-known cat, he was making the point, this is an absurdity. To have a cat which is dead and alive at the same time is a nonsense. This is the point of what he was trying to make. He was saying this is an absurdity. His equation, he was trying to say, he was saying, roughly speaking, my equation does not describe reality. There is something more. And this something more is what we tend to call the collapse of the wave function. Your wave function chugs along and behaves according to the Schrödinger equation very reliably and honestly. And then from time to time, it says, whoops, I'm going to do something else. And then it becomes probabilistic. And it's all hidden in all sorts of mathematical schemes.
So your argument is that classical computation can't explain consciousness. And so the question is, then what can? And this is where you make the fascinating proposal that quantum mechanics, and specifically the collapse of the wave function, might be involved in consciousness.
See, people say sometimes, I just say, well, here's a problem and here's a problem, so they're the same thing. It's not that. It's that we need something which is not a computable part of physics. What is it in the physics that we know that would not be possible to put on a computer? Well, you see, if the collapse of the wave function is purely random, then you could put it on a computer, sort of. And it's not perhaps really random. It's something very subtle. And you need that for the collapse of the wave function. And the story has developed in other ways beyond what I had then. You see, this was the beginning of the story, and you're asking me about the beginning. The beginning was the story. It was a little bit feeble in the sense that I didn't know really much about what to do. I could see that according to my viewpoint, the collapse of the wave function had to be a major part of the physics which is responsible for evoking consciousness.
So to summarize where we are, Roger felt certain that consciousness couldn't be explained just by classical computation. Again, most of quantum mechanics you can easily model on a computer, like the evolution of the Schrödinger wave function. But there's something very weird about the collapse. That's the part you can't compute. So Roger felt he was onto something interesting there. So he sat down and wrote The Emperor's New Mind, and the title, as you might guess, was a reference to the story of the Emperor's New Clothes. The idea being that everyone is assuming we can explain consciousness by putting together enough neurons, but in fact, in his view, the Emperor is naked. consciousness possibly can't be explained by just a bunch of neurons. So I asked Roger what happened just after he published the book in 1989.
I wrote my book, The Emperor's New Mind, and hoping some young people might be stimulated, only got old retired people. I thought I'd done a sort of fairly reasonable job as an ignoramus, but not too bad a job, of trying to learn the main features of neurophysiology.
So Roger started studying up on the brain, really as a side gig to his mathematical physics career. But the more he looked at it, he thought that maybe the macro level at which we were able to study the brain wasn't really revealing its secrets.
But I would say that it has a genuine, deep purpose. And that purpose is not clearly revealed in the structures, but it's not something which is obviously like a computer, something else going on. But I didn't know what was going on. I had no real idea. By the time I got to the end of my Emperor's New Mind, I could have stopped writing in this point, but I thought, well, I've written so much so far, I better go on. And so I more or less thought of some idea, which I didn't really believe. I tried to think of something that might be non-computable, you see.
So that's where things were for Roger's idea. He suspected there must be some kind of quantum effects in the brain, but he didn't know where to look. But at the same time, in America, there was a young anesthesiologist named Stuart Hameroff who was interested in consciousness.
And I got interested in consciousness, and I went to med school and was interested in neurology, neurosurgery, psychiatry, but I didn't like those lifestyles, particularly what they got to do. They didn't actually get to do much. The surgeons did, but the neurologists in particular didn't have much to do. And I took a research elective over summer in a cancer lab and studied mitosis. I figured just try something different. And so we studying cell division. And as you know, the cells divide. The chromosomes are separated by these spindles, which are microtubules.
That's Stuart Hameroff. And while everyone in that lab was interested in the chromosomes where the genes are, he found himself interested in the microtubules. Now, what are microtubules? The starting point here is that all the cells in the brain, like neurons and glial cells, are not empty. Inside every single brain cell is a bustling inner world. You've got all kinds of structures that help the cell keep its shape and transport materials around. And among these structures are microtubules, which are tiny hollow tubes. They're part of the cell's skeleton. Sometimes people think of these like the tracks that guide packages through a warehouse. Now, these are very, very tiny. Each microtubule is about 25 nanometers in diameter, which means you can line up 4,000 of them across the width of a single human hair. And they're long too, so they stretch like tiny straws all through the interior of the neuron. Now, what's amazing is these are constantly assembling and disassembling themselves, almost like living Legos, and this adjusts the internal architecture of the cell in real time. So, Stuart got interested in these microtubules and wondered if they were more than just railroad tracks. Back to Stuart.
Well, microtubules are found in all cells, including neurons, which are full of them, and they're like the skeleton and the scaffolding of the cell, but they're also the nervous system of the cell. They organize things. And their structure, I learned back then, is a lattice, kind of like a computer lattice, where you have individual units, proteins called tubulins, that I thought back then can be in two states, like flexing, like a peanut open and closed, and that would be like a bit, a 1 or a 0.
So Hameroff was looking carefully at these, and he proposed that microtubules might be doing something beyond structural work, that instead of just looking at the microtubule as a roadway, you might think about the details of the microtubules and ask whether this could be a structure that was a lot more interesting than it first appeared. So he started modeling tubulins, the little bricks of microtubules, and came to the conclusion that you could store something like 10 to the 16th bits of information in a single neuron using microtubules. And this was essentially the number that people were talking about for the storage capacity of the entire brain. Now, his colleagues were skeptical.
They didn't want to hear it, told me to get lost. So, except then one day, fateful day, this guy said to me, okay, wise ass, let's say you're right. How would that explain consciousness? How would that explain love, feelings, pinkness, joy, blah, blah, blah? Essentially the hard problem, 5 years before Dave announced it. And, but I knew the problem. I said, whoa, you're right. I have no idea. I was a reductionist and I was ashamed of myself, actually.
So wait, actually, just one second. I want to make sure everyone's following. So the hard problem of consciousness is you've got all this physical stuff happening in the brain. Why does it feel like anything? Why do we have experience? That's the hard problem. Okay,
right.
So you were looking at these microtubules, which are made up of these tubulin peanut-shaped proteins, and you're saying, hey, there's something really interesting here, but it didn't solve the hard problem.
Right.
So, okay.
I was just saying more computation, more information processing. So, and the guy had a beautiful point. And I was kind of stunned. And he said, you should read this book by Roger Penrose called The Emperor's New Mind. I said, I've kind of heard of that guy. So I bought the book, I read it, and I was kind of blown away. I mean, it's an amazing book. The first half is about why consciousness is not a computation. He used something called Gödel's theorem from mathematics, which said a mathematical theorem cannot prove itself. You need somebody or something outside the system, like a mathematician, to say, yeah, it's true or not. And he extrapolated that and said, it's like understanding. To understand something, you need to be outside the system. Very similar to John Searle's Chinese room argument. The guy has the Chinese symbols, he looks them up, and he translates, but he doesn't understand Chinese. So that's essentially...
He's just doing computer operations.
Right.
Yeah.
And so that was the difference. And so the second half of the book was Roger's solution, which had something to do with quantum physics and collapse of the wave function, the measurement problem in quantum mechanics, which was a whole other mystery. And but he said the solution to that mystery is the same as is for consciousness. But Roger didn't have a biological structure that could be at the quantum level. And he said in the book, I don't know what it is. Maybe somebody does. So I read the book and I said, holy crap, he needs microtubules. I've been studying for 20 years.
So Stuart wrote Roger a letter.
But then Stuart Hameroff read my book and wrote back to me and said, evidently, you don't know about microtubules. He was absolutely right. If I'd known about microtubules, I'd say, here's a much better bet. For various reasons. They are partly because they're tubes, actually. It seemed to me that there was a much better chance you could isolate quantum effects.
So they met up in England, and Roger was very taken by the geometry of these microtubules. Tell us what is special about microtubules.
Well, what's special about microtubules is several things which excited me about them. Some of them are sort of peripheral, but not so stupid, maybe. They are tubes to begin with, and that struck me as much better chance to preserve coherence. You see, if you're going to have the collapse of the wave function, you've got to have a well-defined wave function which isn't collapsed by the environment. You see, normally what happens is that the environment collapses it, and that's no use to anybody. The standard, as I say, Landau von Neumann arguments, you say that the collapse occurs because the environment gets involved. You have no control over the environment, and so therefore it behaves randomly in some way.
In other words, he's pointing out that the environment normally collapses the wave function very rapidly, but he appreciated the possibility that microtubules might serve as a waveguide, which means there's something about the particular structure of these long, thin straws that keeps the wave function uncollapsed for a longer time.
A, they're tubes. B, they have a very symmetrical structure of the tubulins, and they combine together in this particular structure, which I found fascinating because it has, for example, symmetries in three different directions. One is along the axis, one is twisting one way, and the other is twisting the other way. So it just struck me, what's funny about these microtubules, you have these microtubules which have one direction along the tube. And that seems to mirror what you get in these nanotubes, that they become superconductive. So this suggested to me that maybe there is some quantum superconductive effect along the tubes, which is quite different from nerve transmission, and which is absolutely a quantum effect.
So the idea is you've got these microtubules, which are inside all the neurons, and these can serve as waveguides. One of the criticisms that people have had about quantum mechanics in the brain is they say, look, it's too warm and noisy in there. Yeah. What do you say in response to that?
Well, that's a general comment. You might expect that applies if it hasn't got some very, very specific structure. And the microtubules, I thought, much better chance of that sort of thing. I mean, they're doing a pretty good trick, you see. If they actually are preserving coherence along the tubes, this is a neat trick that nature allegedly, I'm saying, that is to say, that's my viewpoint, must actually have succeeded and making this trick. I mean, the general comment is warm and messy, sure, as a whole. But there are structures within this warm and messy thing. You don't need the whole thing to be structured in this way. You just need certain elements in this complicated structure, which as a whole may be warm and messy and all sorts of things. But there are things, the claim goes, which can preserve quantum coherence. And the idea is that maybe microtubules do. And when I heard about them for Stuart, I thought that was a much better case than anything I'd seen before.
So Hameroff and Penrose got interested in this possible relationship between microtubules and quantum mechanics. But what does any of this have to do with consciousness? Back to my interview with Stuart. In quantum mechanics, things can be in different positions. The wave function predicts how that moves along nicely. But what happens is you get a collapse of the wave function, which tells you, hey, let's say the particle is over here. And the idea was the collapse, that moment, when that happened, there's some consciousness in the universe.
That's what he predicted.
That's what he predicted. Okay,
Other people were saying consciousness comes from the outside and causes the collapse, but that puts consciousness outside science. It's a dualist position, actually one of the Chalmers takes now. But it goes back to Wigner and von Neumann and Bohr, early part of the 20th century. And then and others didn't want collapse to deal with it, or consciousness, so they just said many worlds. It's easier to think about than consciousness. And Roger came up with a solution, said that the separations are unstable and will collapse and give consciousness. And due to an objective threshold given by the indeterminacy principle, one equation.
Okay, and so who is experiencing the consciousness or the qualia when there's a collapse of the wave function?
The collapse itself is what is experiencing. I don't think, this is controversial, I don't think there needs to be a separate self. Other people disagree with me on that. But I think if you have a sequence of experiences and memory, you have a self, you know who you are, you know when you wake up in the morning, the same person, moment to moment. So I don't think there's any separate entity as the self. I think you have a sequence of experiences, complex experiences. I should go back and say when the objective reduction, that's his name for it, objective threshold, quantum state reduction, objective reduction, OR, when that occurs in the environment, in the chair, anywhere, other than in particular arrangements, the experience is random, fleeting, disconnected. It comes and it goes. It's apparently happening all around us. We never notice. It's like, and that was proto-conscious. So that they call that proto-conscious. And I liken that to if you go to the symphony and the musicians are tuning their instruments before, and you hear all this, to me, noise. To a trained musician, it's different. But to me, it's like, it's noise. And then they start to play. And it's Brahms or Beethoven or whatever. And that's what the brain does. That's what the microtubules do. Orchestrates the objective reduction. Hence the theory is orchestrated objective reduction.
Okay, so when there's the collapse of the wave function, there's a little bit of consciousness. But if you build a device in the right way, where you've got all these microtubules that are guiding this, that are orchestrating this whole thing, then you get something like our consciousness.
And they have to be entangled. So the superposition states become part of one much more complicated state. So when we're collapsing our conscious moments now, there's a lot of richness in it. I see you see me, I see the stuff behind you, et cetera, et cetera. And there's sound, there's different senses. It's all orchestrated. I would say integrated, but that's a different theory. It's more orchestrated.
Now, what would that get us to have entanglement across different regions of the brain? Well, one example Stuart turns to is what's called the binding problem. The binding problem is a long recognized mystery that different regions of the brain encode very different types of information, like movement here and colors here and face recognition and sound and touch. And yet you enjoy a totally unified experience. For example, let's say you're watching a basketball player race down the court, dribbling the ball. different areas of your brain are processing the shape and the movement and the sound of the ball hitting the court, but you perceive the whole thing as one guy racing down the court. The colors and the motions and the sounds don't separate off from one another. So how are these distinct features processed in totally different brain regions integrated into one seamless perception? This remains a central mystery in neuroscience. So how might their theory address that?
Spatial temporal binding. You see something moving through the sky and its shape, color, motion, meaning are processed at different places and different times in the visual cortex and cortex in general. And yet we see one object. We see a yellow kite fluttering, and instead of yellow kite fluttering, we see one thing instantaneously. So it's integrated or orchestrated in time and also in different regions of the brain. So I think the brain needs entanglement one way or the other.
So in other words, neuroscience traditionally just thinks about neurons, and those are, in some sense, quite slow. But maybe, Hameroff suggests, there are much faster processes that are binding things together.
It's more like music. It's more like resonance, harmonics, interference beats. In fact, to get from the very fast to the very slow, interference beats is probably what does it. So I think the brain is more a quantum orchestra than a computer.
Got it. And so essentially all our technologies are just measuring what neurons are doing. Like you dunk an electrode in and you see the spiking of the neuron. And so
they're only listening to the bass and percussion of the symphony. They're missing the flutes and the piccolos and the everything else.
And what makes you think this?
The other theories don't work. All the other theories are based on a neuron firing as a bit, or a neuron is essentially a 1 or a 0. And if you look at a single cell organism like a paramecium, it swims around, it finds food, it finds a mate, it has sex, it can learn. If you suck it into a capillary tube, it gets out faster and faster each time. It's one cell. And it does all that with its microtubules, with its cilia and its internal microtubules. So if a paramecium can do that, are you serious in thinking that a neuron is a 1 or a 0 and that's it? It's an insult to neurons.
So together, Penrose and Hameroff worked on their idea of entanglement going on across the brain. And the hypothesis is that these deep tubes humming away deep inside the brain's machinery, these orchestrate when and what collapses. So they call this orchestrated objective reduction. Give me the idea of orchestrated objective reduction. What does that mean? And how does that explain consciousness, potentially?
Okay, think of I used to play ping pong when I was at school, for instance, you see, and I never achieved any great skill at this, but I can understand that it's a game where you have to act very quickly. And if I flick the ball into the right-hand corner as opposed to the left-hand corner, it's because I think by looking at my opponent that he's not expecting for me to flick it into the left-hand corner. And so I do that flick into that corner because I think from what I've just gained, a very small fraction of a second, much less than half a second, I've estimated that this is a good thing to do. So I think that was a conscious choice. Now, what is the current view amongst, I believe, and I get this from Stuart, the current view amongst neurophysiologists is that these actions are not conscious. They're much too quick. But Stuart's view and mine is that it is conscious. But it can only occur because of the following mechanism. The argument would be that you could preserve quantum coherence at a big level, that it's sufficiently isolated from the outside world, that in this layer, you could preserve a lot of quantum coherence. So that this would mean that the action of flicking the ball this way rather than that way, and this choice, is it made consciously? The current view is there's no time that the consciousness can come about, much too late for this. But our view is no, there is time, because the choice of which action to take can be a conscious one. The action taking involves a lot of nerve transmissions in making your arm go this way rather than that way, and all these things. You think of a tennis player deciding to go cross court rather than down the line, and that involves different muscle actions. Now, those different muscle actions can be in superposition, kept in superposition. So which one of them is triggered can be done very quickly. And then the actions take place and the person does what is decided to be done. So although the conscious action to move all those particular muscles like this, that's not conscious. Yeah. What's conscious is I'm going to flick the ball to the right rather than to the left. And so that is a whole lot of different motions which are all together in superposition. So this is the idea that this collection of motions and that collection of motions and which ones are activated are all there together, and which one is activated is a conscious choice. And that conscious choice, as it is at a quantum level choice, in these very specific cells, that you get the coherent superposition of different actions.
I see.
So it could be this action is under control, or this one, and they're all there in quantum superposition. So the choice you make as to which one is controlled is a quantum choice.
And presumably, when the waveform collapses, that's when you become conscious of something. That's the idea, yes? That's when
the consciousness is to do with the actual collapse.
One intriguing thing is that this proposal seems to blur the line between physics and philosophy in an interesting way. So if consciousness arises through quantum processes, does that suggest that consciousness is not just a feature of brains, but a more fundamental property of the universe? How do you see that?
Yes. But you see, it might be you've got to get it organized in a very subtle way in order to reveal. You see, the collapse part of it might be easy to reveal, but the way in which it's not quite random, and quite random probably in a very sophisticated way.
Does this hypothesis have implications for free will?
That's a very good question. You see, I've even quite recently sort of changed my view on this question. I often thought it's a sort of meaningless question in a way. I mean, does it mean that a quantum effect is brought into play because quantum thing is not deterministic? And does the fact that it's not deterministic mean free will? Not normally, because it's random. And if it's random, that's not free will. I mean, you're just tossing a coin. It's not random because it's got to be doing something. I mean, randomness isn't beneficial in a way, you see. You could make it random, but that's not the point of free will. You could say that, you see, people often say that free will could be there if it's not deterministic. But it doesn't do you any good if it's just random.
Yeah.
So the view I have is more or less this. It's not even one I heard. It's a fairly recent view, I think. But the view is more this. There is something retrocausal about it. What free will really means, and what I'm arguing for here, is not that you can do anything you like, and you can act randomly if you like. You're doing what you think is the right thing to do. So you have the free will to do what you think is the right thing to do. And that doesn't necessarily mean righteous in the sense of virtuous. It means in your judgment, the correct thing to do. Whether it's correct just for your beneficialness or for the good of the whole or whatever, that's not the point. The point is that you are doing it because you think it's the right thing to do. Now that means you're understanding it.
What kind of experimental result would excite you most in the coming years?
I think if you're looking at things plausible within the current technology, maybe some convincing kind of quantum coherence within microtubules.
I want to ask you about AI. We've seen such incredible progress in classical AI systems, but given your view that consciousness involves non-computable processes, do you think that AI is conscious, could be conscious, or is it just an impressive simulation?
No, in one word.
Okay.
It's not conscious.
Okay.
And it's not going to be conscious by having more and more and more elements in your computer.
So could a quantum computer in the future, could a quantum computer be conscious if it were designed with the right architecture, or is something else still missing?
You have to be careful about what you mean by a quantum computer, because I don't think quantum computer, in the sense that people use that term, does actively involve using the collapse of the wave function as part of the mechanism, in quotes, because it's not really a mechanism.
That's right. Yeah, okay, got it. So the kind of quantum computers that, for example, Google is working on now, because presumably it doesn't involve the collapse of the wave function, you think it wouldn't be conscious as such?
Yes.
Is that right? Okay,
That's
great.
correct.
I asked Stuart the same question about whether contemporary AI could be conscious.
Not with the kind of computers we have now. Not with a silicon-based. And, our friend Dave Chalmers, after decades of the heart problem, recently came out and said, well, AI consciousness is inevitable. And throwing the heart problem under the bus. Totally.
Interesting.
And then backing up. And when I questioned him about it, he said, well, what's the fundamental? There's no fundamental difference between silicon and carbon. I said, wrong answer, Dave. First of all, it's not carbon. It's organic carbon, which means aromatic rings, which means quantum. And there's a huge difference between organic carbon and silicon. Silicon can't do that. And this organic carbon, aromatic hydrocarbons, have been in the universe right from the start.
So let's summarize. According to this idea from Penrose and Hameroff, the brain isn't just a network of firing neurons, it's also a kind of quantum computer. Inside every single brain cell is a whole world of microtubules, these tiny cylindrical structures that are so small they've traditionally been ignored, but maybe, they suggest, these structures are doing more than organizing the cell's interior. Maybe these microtubules are hosting quantum processes. Maybe they're sustaining delicate quantum states long enough to do something meaningful and entangling across cells, and that the collapse of these states might correspond to moments of conscious experience. Now, I just want to repeat one point. You might be thinking, wait, doesn't quantum physics get washed out in warm, wet environments like the brain? That's a reasonable objection. In fact, it's one of the main reasons that many scientists have been skeptical of the orchestrated objective reduction theory. Quantum coherence usually does not last long in messy biological environments. It's fragile. But on the other hand, that skepticism has been challenged in recent years by findings in other parts of biology. Quantum effects have now been observed in photosynthesis, in bird navigation, in the sense of smell. Somehow, living systems might be more hospitable to quantum phenomenon than we thought. And if that's the case, then maybe, just maybe, the brain has found a way to leverage quantum effects, not just for computation, but for consciousness itself. Now, Penrose and Hameroff's theory and others like it remain highly speculative. Neuroscience continues to make great progress without invoking quantum mechanics. Artificial neural networks, which are entirely classical in their architecture, these have achieved unbelievable feats like the modern blossoming of AI. But, so far as we know, artificial neural networks like ChatGPT are not conscious. And so the idea here is that we need to think not just bigger, but perhaps also submicroscopically smaller. So we've just heard from two thinkers who aren't afraid to step beyond the comfortable borders of their fields, to probe around in areas that most scientists won't touch. What I find so compelling isn't the certainty of the theory, it's the audacity of the question. It's the willingness to say, look, perhaps our current tools aren't enough. Maybe consciousness isn't just a clever computation, but something much stranger. Maybe the deepest puzzles in neuroscience can't be solved without rethinking everything from the ground up. There's a long history of big leaps in science, beginning with questions that sounded naive or mystical. There was a time when most of the ideas we take for granted today were ridiculous. So I want to return to one last thought from Roger. What advice would you give to young scientists who are drawn to the big, risky questions about consciousness, but are afraid to step too far outside conventional boundaries?
Try and do the following. You will have some specialist view that, you see, in order to make progress, you've got to dig deeply in a certain area and understand that area as well as you can and better than most other people. But you also, at the same time, should keep a broad outlook of what's going on in the outside world and pick up, maybe, if you see something which might connect with what you're doing.
There are plenty of critics of this idea who point out reasonably that there's not enough experimental evidence to take this idea with the requisite seriousness yet. But it's okay to explore the speculative as long as we keep one foot planted in the empirical. The key to making progress in science is balancing skepticism with curiosity and openness. All of us in neuroscience like to believe that we're close to cracking the puzzle of consciousness, but the fact is we're probably just at the foot of the mountain. And it's always possible, just like in any field, that we're not even asking the right questions yet. What if we've been looking at the hardware in an incomplete way and missing the best tricks of physics? The fact is that the central mystery of neuroscience, for which no one has a good answer, is the hard problem of consciousness. Why, if we have an organ that goes around and collects information, no different than a camera or a microphone, why does it feel like something, presumably in a way that your iPhone does not when it makes a recording? Why do we have private, subjective experience of the world? Quantum mechanics may or may not provide the answer. Maybe we're all just shooting in the dark until we discover a new field in 100 years from now called schmontum mechanics. But whatever the case turns out to be, it seems likely to me that the neuroscience textbooks used by our great-great-grandchildren will have very different stories than we do today. And future centuries will look back on our scientific frameworks with the quaintness that we look back on ideas of phlogiston or spontaneous generation, or that the Earth was at the center of the universe. But the only way we're going to get there is to keep digging deeper and asking, by not falling for the assumption that we've got it all figured out with our standard textbook models, but by continuing to propose and put to the test brave new hypotheses. Go to eagleman.com/podcast for more information and to find further reading. Check out my newsletter on Substack and be a part of the online chats there. You can watch the videos of Inner Cosmos on YouTube, where you can leave comments. Until next time, I'm David Eagleman, and this is Inner Cosmos.